Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GG2 Cloud. And today we will be going over an exercise together, namely one on pressure drop calculations. Now, I also want to say this is our last video of 2025 with educational content. We have made over 50 videos this year, so I hope you will enjoy this last one as well. Because holiday season is coming near, so we selected a more romantic scene for this exercise, namely a fictitious case of a bookstore renovation in the old city center of Bremen in Germany. So we have a corner bookshop with some apartments on top of it, and we're going to renovate this whole building with some geothermal energy. And there is some space nearby where we can install a bore field and we can decarbonize the heating and cooling of this building. And the goal of this exercise is to learn you something about, first and for all, how you can calculate the flow rate, because in all other exercises I always gave you the flow rate. Now we're going to estimate it ourselves. We're going to look at the pressure drop in the horizontal pipe. We're going to take a look at the difference between single and double U-tube in this context. We're also going to use our latest method just released last week, where we can automatically calculate the required depth and bore field size. How has this to do with turbulence, with pressure drop, etc. So quite a lot to discuss. So let's go over the input parameters real quick. We will design for 20 years within a temperature range of 0 and 17 degrees Celsius. For our ground parameters, we will use 1.9 watts per meter Kelvin in the city of Bremen. So we use the temperature database there for the Deutschland Bremen. The input parameters, the bore field tool will start with its 3x4, 6 meters apart and 120 meters deep. For borehole resistance, we'll start with a double DM32 new probe. And our fluid parameters are 25 volume percent monopropylene glycol and a delta T of 3 degrees across the heat pump. Now, in a second, I will show you or explain to you how we can use this type of information to come up with the flow rate of a system. But for now, we don't have a flow rate. We just have a temperature difference across the evaporator of the heat pump and across our bore fields. And for our loads, typically bookstore, it's rather high temperature. We have 67 megawatt hours per year of heating demand, 37 kilowatts of peak heating, and for cooling it's 4 and 2.9 kilowatts and megawatt hours respectively. The efficiency in heating is also 5 and in cooling it's 20. So this is general information for the design of the bore fields. Now for the pressure drop, as you perhaps recall from our videos on that topic, we also need the longest horizontal path, so the worst case scenario for the pressure drop. And for our project, that's the borehole located at the bottom left. And this is the path that will take to the main manifold in the building. So it's 6 meters, and then another 18 meters. So a total of 30 meters is our horizontal connection. Now, before we jump into the software itself, I want to say a couple of words about how we can estimate the flow rate. Because there are different assumptions, different cases when you're designing bore fields. For example, when you're a driller, sometimes you have an engineering firm who did a simulation for you, and the flow rate is a given. It's just, this is the flow rate, deal with it, calculate with it. That's one option. It was also the option you had in the other exercises on this channel where I gave you the flow rate, so it's a given. The other option is to use or to take a look at the technical documents of the heat pump. Typically there is also some pump characteristic and you can see, okay, this is my flow rate. This is the nominal flow rate of my heat pump. This I can use to calculate my heat transfer in the ground. So technical data sheet of the heat pump. But perhaps you are in a feasibility phase or the heat pump is not yet selected, and yeah, you have to make some assumptions. And there you can either rely on saying, okay, we have a flow rate of 0.3 liters per second per borehole. But the problem with that assumption is that when you're changing your number of boreholes, so you go from 12 to 10 boreholes, for example, the total flow rate through your system also varies, which is not what happens in reality, because there your flow rate is actually determined by your building demand and your heat pump or your cooling demand, and not so much by the number of boreholes. So therefore, it's better to rely on a very famous equation in heat transfer, namely Q is mCp delta T. So what this is basically a relationship in all of heat transfer, basically between the power of a system, the emission power, extraction power, whatever, and the flow rate and the temperature across a certain element. So the Q in this formula, it's not so much the peak power of the heat pump. So for example, if you have a heat pump of 30 kilowatts, this 30 kilowatts is what's been given to the building, but from the ground, yeah, there is only 80% of that. And because you have the efficiency of your heat pump, which also takes part of the heating on itself. So if you have 30 kilowatts going to your building, there is only 24 coming out of your ground. There's 24 kilowatts of extraction power. And it's this extraction power that you need. The flow rate we will calculate. And it depends on also the specific heat capacity of your heat transfer fluid. Now, in theory, this is not a constant because it depends on the temperature of your fluid, because the viscosity, the density, etc. it changes. But also for different type of antifreezes, it typically is around 4 kilojoules per kilogram Kelvin, I would say, between 3.7 and 4.3, something like that. So 4 is a good first estimate. And then you have your delta T across your bore field, across the heat pump evaporator, which is typically between 3 and 5. Depends a little bit on the manufacturer. In our case, we will take 3. So given this presumably constant, or we will assume it's a constant, given our delta T, given the peak power of our heat pump and the efficiency, so we can calculate the extraction power, we can calculate the flow rate of the heat pump. So now we know that. Let's jump into GHG tool, plug in the numbers, simulate, and see what insights we can get from looking together at this exercise. Now, if you want to get the most out of it, I suggest you stop this video, take a look at the article, you try it yourself, play around a little bit, and then come back and see how we did it together. So looking forward to seeing you in a second. So here we are in GHG Tool Cloud. I created a new project. Now let's populate it. So we have a minimum design temperature of 0. And for a pressure drop, we will start with all the boreholes in parallel as a first calculation. So both Tickelman and series are set to 1. And then we have our furthest distance, if you recall, was 12 meters up and 18 meters horizontally to the manifold, so it's 30 meters. Let's use a DN40 for that. For ground it was 1.9 and it was located in, not in Wien, but in the city of Bremen in Deutschland. At Borefield, the borefield was 3x4 with 120 meters of borehole depth and 0.7 meters of bury depth. Then we have our borehole resistance, so we start with W tube as a first calculation, 25% of monopropylene glycol. And then let's calculate now our flow rate through the entire borefield. So let me open up my calculator app. So this is the calculator app. So we know that we have a heat pump of 37 kilowatts and we have an efficiency of 5. So this means that 4 out of 5, so 80% of the energy that goes into the building, it comes from the ground. So if we multiply this by 0.8, so 80%, we know that we have just short of 30 kilowatts coming from the ground. 37 in the building, 30 coming from the ground. So if we divide this by all 4, or constant, assumably constant for the specific heat capacity, if we divide it then by 3, we have 2.5 kilograms per second of flow rate to the entire borefield. So let's use this 2.5 kilograms per second. And for thermal demand, it was 37 kilowatts in heating, 67 megawatt hours. For cooling, it was, let me speak, 2.9 megawatt hours, and 4 kilowatts. So let us go ahead, send this to the server, and calculate our first scenario. So we can see that we are just slightly below the threshold of 0 degrees. We're in a laminar state with a rather good pressure drop across a single borehole. Also from the borehole to the manifolds, it's 2.7, so we have a rather low 15.8 kPa flow rate through our entire system. Now that was a first scenario, but typically, or what sometimes happens is, let's call this Tichelman, is that we say, well, let's keep everything in parallel, but we want to limit the number of horizontal connections, because these piping, these wells also cost quite a lot. So what we can do is we can connect the boreholes in numbers of 2 to the main manifold, which means that we only have 6 horizontal connections now, which also means that the manifold can be a little bit smaller. So that's also good for economic reasons. Of course, the temperature does not vary. The pressure drop across our borehole is also the same, and because in Tichelman, our reverse return, the flow rate through each borehole is still the same. But now our horizontal pipes have a little bit higher pressure loss, 10.19. And what you can see is that this jump here, I will move away my cursor, it indicates where our horizontal pipes go from laminar to turbulence. It's this jump, and it's just below our 2.4 liters per second, which we have now. And in our previous case, it's here, so we don't have any turbulence in the horizontal connections. Now we have, which is also why we have a bigger pressure drop in the horizontal circuit. But as you can see, thermally it's still the same situation. Now we are quite laminar, 840. It's extremely laminar. So what we perhaps can also investigate is if we say, okay, let's not go for a Tichelman connection, but let's go for a series one. Where we say, okay, instead of connecting them in groups of 2 in Tichelman, let's connect them in series. So basically what we do now, we still have 6 horizontal pipes, but now we go into one borehole and then into the next before we return. So this means that a flow rate for each borehole is twice as high as it was before, meaning we have better heat transfer. And this you can see, we're still laminar, but already quite higher Reynolds number. We also now are just above a temperature threshold, which is good, but our pressure drop is way higher. So we came from 13, we now have 25, which is almost double our pressure drop. But the pressure drop through our entire bore field, it's even higher, because at 25 85 is the pressure drop across one borehole, but since they are connected in series, we have to sum the pressure drop. So we have our horizontal connection, which is still 10.14, and the same flow rate goes through it as in our Tickelman connection. But now we have to sum this with 2 times the pressure drop across one borehole, which gives us a total pressure drop across the system of around 62 kPa. And we still have our laminar flow rates. Now, what could be interesting to take a look at is then to see what happens when we go to a single DN40 probe. Because perhaps you recall our discussion between single and double U probes, and you recall that there is a range in which our single U, single DN40 in this case, will outperform the double one. Because if we go to our borehole resistance step, here we have a certain amount of cross-sectional area where the flow can go through. If we go to a DN40 and a single one, this is smaller, meaning that our flow rate, as is already indicated here, is transient. It's between laminar and turbulent, giving it a better heat transfer rate. So in our results, we also see this clearly, that now we are in a transient state and we have risen to 0.2 degrees Celsius now. It's not a very significant difference, but in cost, perhaps it can be that this solution is actually cheaper. The pressure drop across our borehole has also increased from 26 to almost 40 kPa, and since we're still in series, the pressure drop of our entire system at this flow rate has also increased to just short of 90 kPa. Now, this is a little bit the insights you can get from playing it around yourself. But now, what would happen if we just give the inputs to the software and say, okay, this is my flow rate, what can you do with it? So, as a next step, we're just going to explore what the optimal solution will be. So we use here calculate rect size depth. So now in our general tab, we just go to calculate required size and depth, and that we discussed last time. So now the algorithm will find the most ideal situation. Let's set this hydraulic part off for a second. We will calculate the optimal number of boreholes given the flow rate that we have, and we will minimize the total borehole length. So let's vary between 50 and 200 meters. And for our borehole resistance, let's say, well, let's not connect them in series. So we had before a laminar flow rate, if you recall. It was only because we went to series that we go to this turbulence. And now send this to the server and let it try 100 different combinations. So here we are, and as you can see, it lowered the number of boreholes rather significantly. Yeah, we were at 12 boreholes, now we are at 6, which has a couple of advantages. Namely, our average undisturbed ground temperature is now higher, and because we are drilling deeper, so it's higher. But also secondly, it optimized the number of borehole length in such a way that since we have less boreholes, our flow rate is now transient. So also our heat transfer is better. But since we're now not in series, we know that the pressure drop across one borehole it's now higher, because instead of having 12 boreholes, we now have 6, and this is the pressure drop across one borehole. But what is important is that we now have 1,100 borehole meters instead of 1,400. So that's a rather significant difference. Now, as a last resort, I just want you to show you what happens. Let's call this 2. When we would have said, okay, instead of keeping the flow rate to the borefield constant, let's work with the flow rate for each borehole and we know that we started with 12 boreholes, so we have 0.205 kilograms per second through every borehole. So if you now simulate a scenario, which is typically the assumption that you say, well, this is the flow rate through each borehole, you will see that you will end up in a totally different configuration, because now the algorithm does not care how many boreholes there are, because the flow rate is the same in every borehole. So it will just take a look at the depth. And this you can also see in the results. Yes, so we now have 7 boreholes, even slightly deeper, but we have a significantly higher total borehole length. Also lower pressure drop, of course, because we now have a way lower flow rate through our system. We said, well, this is the flow rate of 0.205 to our entire per borehole when we have 12 boreholes, but now we have only 7. So yeah, of course, the pressure drop is low because the flow rate is also lower. And that's so something you have to take into account. If you use this methodology to automatically calculate the number and the depth of the boreholes, please work with a flow rate for the entire bore field, because otherwise you will make mistakes. So I hope you found this video interesting. I hope you found the other videos in this here interesting, and please consider subscribing or liking this video. If you have new ideas for videos or you want to have certain features implemented, please contact us and we can see what we can do for you. I'm also looking forward to seeing you in our next video. Take care. Bye.